Welcome back. A couple days this week of classes and then Easter break for the college. The next homework will be posted soon, and we'll be due the Wednesday after that. Right. We're going to have Monday, Wednesday to talk about progression, correlation, look at examples, and then over that longer weekend. Yeah, so there'd be Tuesday office hours and so on. So if you have questions on the homework, there'd be some time to send an email or come in for questions before that. While this is going on, even though there's these breaks and not a high density of homework assignments, there's still projects. So if you think about the project and maybe get a data set, that'd be great. You know, if you would like to do a topic in a certain area or thinking about something and want to ask if I have any ideas or you can kind of point in a direction for something, or if you find something that you think might be good and just want to ask, does this look good? I'm thinking about doing this. I can look at it quickly and maybe give a couple of pointers. But where you say if you have an Excel spreadsheet and need to get it into R, something like that, you could send it to me and say, I'm not sure how to get this into R, and maybe I can help with a little bit of that process. Right? So that you can get it, have it ready, so that when you do have time in your schedule with everything going on, it's ready to go so you can work on it. Today and Wednesday we're going to look at regression and correlation. So we're predicting a variable from another and looking at linear association. So the type of data that we're going to look at in this example, one of the data sets that comes with ours is called Old Faithful. The example is called Faithful by Old Faithful Data Geyser. Old Faithful Geyser is in Yellowstone National Park, and it's a big geyser that's been erupting for, I don't know, hundreds of years. And has anybody been there and seen it or traveled out there? So it's pretty fun if you can go camping. There's a hot magma below the surface of the earth is heating water that's accumulated in tunnels and pools underground. It builds enough steam and then suddenly it bursts out. And the Old Faithful, about every 90 minutes, erupts. And if you go, there's a big lodge where you can stay or you can go camping all over the place. And there's a sign there that says the next eruption is in 35 minutes, plus or minus something, right? So it gives this little interval that you should be there. So you can walk around, see other stuff, get a hot cocoa or something, and then go and wait without missing it. And so this data set has 272 observations where they measured the eruption time. How many minutes did this thing that's, it's tens of thousands of gallons of superheated water are shooting into the air. And then the waiting time until the next eruption. And think about, in the 1980s, they didn't really have much barriers around this, so people could come up and stand like really close to it. It was like, it's scalding and dangerous. Now you have to stay back like a long way. But this is what the data looks like in this case. Right? Bigger, right? So there are eruption times, 1.5 minutes, 2 minutes, 3 minutes, and so on. And then how long you have to wait till the next one. So how would you describe this relationship?
Yeah. Like a positive relationship.
Yeah, it's a positive relationship, right? The longer the previous eruption, the longer you tend to have to wait there. And there's some some chemical analysis, reason for that. If there's water that's dripping into these caverns at a certain rate and it's heating up at kind of a certain rate, and it takes a while before you get enough pressure before you get a big explosion. And so if you get a real big explosion, it empties out and takes longer to fill up and build up the pressure, so there's some rationale for thinking that would be the relationship. So we can simply describe the relationships. Between our two variables x and y. Both of these we're thinking of quantitative relationships. And so generally x on this axis and y on this one. Right? What shape is it? Is it positive or negative? In this case, for the Old Faithful, so eruptions in minutes versus waiting time, also in minutes. Generally, there's kind of a clump down here, another clump up here, right? But it's generally positive. You can use words from your vocabulary to describe the strength of the relationship. So strong, moderate, weak, etc. For this data set, how would you characterize that one? Moderate. Moderate to pretty, just moderate to strong, right? It's looking over many different things. I mean, so this kind of a mechanism of this biological, chemical mechanism, natural mechanism. It's pretty, I would say, it's pretty strong. A lot of things in social science, economics, psychology, measuring things on populations, are a lot weaker, a lot noisier. A lot of biological things are a lot noisier too. They're just not associated with each other so much. Right? So I would put it more on the strong side, but depending on your point of view, it might be moderate, right? You can look for nonlinearities. Nonlinear versus linear. So linear is just the word that means it's a straight line, generally. Some things go up and then they slope down. Some things are curving. Some things are going off at angles. And it's just not straight. Sometimes things that are related to area or volume or squaring or cubing things, and then it's just not straight. Right? Some things don't increase. Sometimes miles per gallon, gallons per mile, and weight of cars and things. It's not really a straight relationship. Sometimes you need to square the force or acceleration to get it going, and so it doesn't follow a straight line. Other things are more haphazard. Sometimes in these relationships there's going to be outliers. There'll be some point that's just an oddball. And you'll see it there and say it's kind of deviates from the overall pattern. We don't have too much of that actually in this case. They're all pretty much kind of doing really consistent with the pattern in this case. But many times there's an outlier, and you can note that. One other aspect of the pattern is kind of important or interesting here. Kind of got two clumps. Right? There seems to be, eruptions that don't take so long, and then other big ones. So there kind of be this kind of tipping point or something going on in there that's much less likely to happen. If this is really just random selection of data, something that's in there. So that doesn't fit within so much of any theory, but it's kind of interesting. Statisticians might fit something called a mixture model to that, to have two different distributions, but in any case, that's something else. The correlation describes the strength of the relationship. Correlation measures the strength of the linear relationship. And correlation is going to be a measure typically called R, little r that goes between -1 and 1. When R is 1, then you're going to have all your points directly on a line for positives. They're exactly on the line. It's actually 1. There's no deviation, no error. That would happen if you're doing something, converting one set of measurements from inches to centimeters. There's an exact relationship, no deviation. Or changing between currencies, assume there's no fees or loss or something like that, between pounds and dollars. It's just a straight ratio relationship. If it's going down, going straight down, the negative slope right on the line, right there. R equals 0 is there's no overall linear association. It can can be just kind of a random scatter of points out there, just no up or down. You can have other funny things happen. You could have something that kind of goes up and then goes down, right? Well, then X and Y are going up for a while and they're going down. If that's exactly balanced, there's no linear association. So you still get correlation of 0, but it's a little funnier case. Most of them fall somewhere in between. Right? This particular one has a correlation of 0.90, so 90%. So it's pretty high up there on that scale between -1 and 1. The formula for this, mostly we'll compute this from the calculator, from the computer, or look at plots versus different pictures. It actually takes the deviation of x from its mean times the deviation of y from its mean, and divides by the standard deviation of x, and standard deviation of y. And that's correlation. I guess maybe 1 over n minus 1. I need to average it out there. So R is that whole thing. And so you think about this numerator over all the points, and you put kind of put x bar here, put y bar over here, and you're going to look at the deviations of x from its mean and y from its mean. Consider a couple pictures. You have that type of picture of points, and another picture would have points that are going this way. And what does this numerator, what type of things does it compute, add together in these two cases? Well, like in this case, for a point that's up here, what is xi minus y bar times xi minus x bar, yi minus y bar? Is that going to be positive or negative?
Positive.
Yeah, so if x is bigger than its mean, then y is bigger than its mean. That cross product up there is positive. And in this sector down here, x is less than its mean, and y is less. So xi minus x bar is negative, yi minus y bar is negative. So it's a negative times a negative. So it's again kind of a positive contribution. So most of the points would be adding something into that numerator that'd be positive if it's sloping up like this. On the other hand, well, here x is bigger than its mean, but y is less than its mean. So it's a positive times a negative. So most of the points that are down in this area are going to be negative contributions to this top up here. And similarly up in this quadrant. Most of these points will have a negative contribution up here to give this negative correlation. And so it's that balance of those. How big are the ones that contribute positive or negative? For Old Faithful, I agree that 0.9 is generally a strong correlation. People give guidance, but I think it's really depending on the field. Like if you work in some physical chemistry or physics or something, you could get correlation to 0.99, right? Because you're dealing with physical laws and balancing equations, and except for a little bit of measurement error or experimental error, it's basically perfect, right? But social science things, negative 0.1 to 0.1, negative 0.2 to 0.2. Yeah, you can get quite small things. It's still meaningful. Explaining, 10 or 20% of a sociopathic or other economic behavior is a big deal, but it's a much smaller correlation. And it's kind of field dependent. We are going to look at predicting, right? So if you're there at visiting this place and want to know when is it going to erupt, right? We want to predict y. Based on x is the general goal. Based on x, and we're going to do linear prediction. Meaning that we're going to find a line linear equation. Some constant a plus some constant b times x will define a line for us. So here's x and here's y. And this line is, if b is positive, right, or positive slope. A is this intercept. A is the y-intercept value, and b is the slope. So as x changes for different values of x, so different waiting times, or different eruption times in this case, if x changes by 1 unit, then y is expected to change by b units. And so if it's a ratio of b is 2, then 1 minute extra eruption time would mean 2 more minutes average waiting time. And so we're interested in finding A and B to predict, let's spell that Y well. So we want to find A and B such that for our points, we get, here's kind of our point. We want some line to kind of go through those such that we're predicting pretty good. So that's the route. What does it mean to predict pretty well? And so what would you say? I mean, how would we measure success? How would we say that a line is reasonable or good for predicting? Maybe not mathematically, but maybe conceptually. What would you think it should do?
That all the values should be really close to the line.
Yeah, you want these points to be pretty close. Yep. Some of them, if you have a few a little more spread out, you can't go as close to all of them, right? You kind of need to balance all the points in there together. And we're focusing on y as the outcome. It's predicting y well. So we're going to look at draw these pictures a few times in this. When I teach the course on this and different related methods, I end up drawing a lot of pictures. So we're going to draw some line in here. And we're focusing on doing well in terms of predicting y. So we look at vertical distances. We look at these differences here, from the points to the line for all of them. So what we observe is our xi values and our yi values. And our predictions, or fitted values, y I have, we put a little hat on it. So you give me values of a and b, and for any value of x, you put it in there. It tells you what the prediction is. The error, or sometimes called residual, is e, yi minus yi hat. So that's the little vertical distances. The vertical distances in red there are those little errors. Sometimes the points are above the line, and sometimes the points are below the line, so some positive, some negative. So what we're going to do is square them. Squared. And we're going to look at the sum of squared residuals. It's the sum over all the points of ei squared, without the summation of e1 squared plus e2 squared plus e sub n. Add up all those squared residuals. And what you get to do is you get to move the line. You can move it up a little bit, down a little bit, you can tilt it differently. And as you make any change to that line, you get another sum of squared residuals. And we want to find the solution that's best. We want to minimize that. So we want to find the values of a and b, that's going to define our line, such that averaged over all the different points, or summed over all the different points, it produces the smallest sum of squared residuals in the y direction. And there's a solution to that. It's called the least squares solution. Calculus solution. You have this thing bi squared. This yi is a function of a and b. You take two derivatives, partial derivatives. You get two equations, set them equal to 0. Solve those two equations for the two unknowns, and there's an explicit solution. The solution is v ends up being the same thing up there, minus that we had for correlation, the numerator, over the standard deviation of the sample variance of the x's. Another way of expressing this solution, this analytical solution, is the exact solution to this problem, is the correlation times the ratio of standard deviations. And then once you calculate the slope, then the intercept is calculated as this value, this equation. And so putting these two together, our predicted value is A plus B times this. We won't do much of this by hand, but we'll do it with a computer. But that's what it's doing. So B is related to the correlation. If it's positive correlation, we're going to get a positive slope. If it's negative correlation, we get a negative slope. And then it has to adjust for the units of measurement of x and y. So in the regression, there is this command. It's called LM, linear model command. Right? And this is the syntax that this computer program uses. Right? So the variables are called waiting time and eruption time, waiting and eruptions. And this little tilde in there means that this is y as a function of x. So waiting time is a function of eruptions. So on the homework, when you do this, I'll give you some guidance. But on a project, you can think about, do you want this is y and that one's x? And the data set is there. And so LM, it's a little letter L and M, linear model, meaning to do this linear model. The basic one in this and other programs is ordinary linear regression, and then it summarizes it. So when you run that, it gives that information there. It gives a little description of the residuals, minimum, maximum residuals that come with that. So that just produces this output here. It tells you what command you're doing. It gives you a little summary of the residuals, and it gives this stuff here. Coefficients, estimates, standard errors, t-values, and these are p-values. We're testing something. And so we're going to try to understand what this stuff is today. There's a bit more down here that we'll try to take up on Wednesday. We might talk about a couple of things there yet today. So, but it gives, and then under this estimates column, it gives you those two solutions. It gives you those two coefficients, right? This is A for the intercept, and instead of calling it X or B, right, it gives the variable name, the eruptions variable name as the predictor. So what this is giving us under the estimates column, right, it gives the intercept value of A, and then it gives us the slope B, but it refers to it by the variable that is X. So X was the eruption time. That is there. So we get the 33.47 minutes intercept, and then an eruption, 10.73 slope. Right? So our equation then is 33.47 plus 10.73 times x, where x is the eruption time, and this is the predicted waiting time. So if it erupts for 2 minutes, right, how long do you think you have to wait until the next one? So x equals 2 minutes of eruption. So from our, look at our graph a little bit, you can actually put that line on there with a little command. Down here just after that, if you plot it, that's the linear model command. This AB line was a linear model line command. And it will just take the coefficients from there and put them on. That's the predicted line there. And so if x equals 2, that's fine. Our y hat, kind of doing it this way, 33.47 plus 10.73 times 2, y hat is about 54. So if you put x and y hat on there, this changes the sign there. Let's make it green. So there's the predicted value. It's make it even a little bit bigger. I've used this a while, so I know some of these little commands. It's not numbers, right? So that's the prediction, right? When x is 2 on there, and this would be the calculation, 33.47 plus. So that's the predicted value. That's on that one. Any questions? So if it was 4 minutes for x, you put it in, it would come up here. 5 minutes, it would come up here. What if it erupts for 8 minutes? Are you going to use this equation to predict for 8 minutes? If it's linear still, right? If this line would continue, right? And somebody told you it erupted for 8 minutes, how long do you have to wait? Well, you can do the calculation, you put 8 in there, right? But maybe something has happened. If 8 is completely outside of the range of normal data, maybe the thing blew up. Every once in a while they blow themselves out and are destroyed. So often it's best to just kind of predict within the range where you actually have data, because it's less extrapolation. Extrapolation has a little risk that maybe things have changed outside of there. Not the same relationship. But in any case, so there's these estimates, but there's these standard errors and t-values. So there's some model, there's some parameters in there that we want to know. Right? All right, so you can think about what is the real relationship in this? How does it biologically, chemically actually work? These are estimates based on 272 points. So there's uncertainty. How confident are we in this slope, 10.73, where 1 minute more of eruption on average gives us 10.73 minutes more waiting time? So we can do statistical inference. Primarily we're going to do statistical inference for beta, for the slope. You can do inference for the intercept. It's kind of included in the output, but often the focus is on the rate of change, how things go. So the formula is you have your estimate, right? So this is the sample estimate. Sample estimated slope. There's going to be a t-value in here. It's the upper tail with n minus 2 degrees of freedom instead of 1. And then a standard error for this one. Now in this case, we had 272 observations, so our degrees of freedom is 270. And the upper tail for a t for 95%, which is 95% confidence interval, is about, with 270 degrees of freedom, is about 1.97. It's just a little bit bigger than a standard normal. And the rest, the estimate and the standard error, come from the computer program. So the computer program here has standard error estimate, 10.73 for the coefficient on slope here, and it's standard error. So this already incorporates estimates of variabilities, the effective sample size, the variability of the x's, everything's already incorporated there. So out of that output, this one is 10.7. One moment to the next, 10.73 plus or minus our t-value, and then 0.3148 goes in here. And it's about 10.1 and up to 0.4 from what I calculated before. And so that would be our 95% confidence interval for the slope. What is the interpretation of the slope in this problem?
95% of the value will go off. Exceedingly not range.
Yeah, so 95% confidence that the slope is actually in this range. The slope has to do with how many minutes you think you're going to wait, depending on how long the eruption is. Right? So 1 more minute of waiting would give you somewhere between 10 and 11 minutes of, so about 1 minute of eruption, or 1 more minute of eruption, would give you somewhere between 10 and 11 minutes of waiting time until the next one. So interpretation of slopes are a little bit, in context. You have to talk about the change of x and the change of y. It's a little bit more involved with that. So you can make a confidence interval based on that. And I think there's a command that it's a common thing to do. So instead of repeating this thing, right, you can just assign that linear model object to some name, just mod, short for model. So summary of mod gives me all that output I had before. And then there's a confidence interval for mod. Let's see what that does. Yeah, that gives a 95% confidence interval for eruptions. That's a 95% for confidence interval for the slope. And this is a 95% confidence interval for the intercept, if you're interested in that, right? So there's some uncertainty about what it would be here. Now, of course, you're never going to have a 0 minute eruption, so we're not really interested in that so much. We're more interested in this rate of change, because we don't want to miss out on the next eruption. The predicted points, we calculated it for 2. You can actually do them all at once, and then put them all on the line. These are all the predicted points for every single value of x that we have. So in this case here, when x was just a little bit more than 3, that's the predicted value. The circle there is the observed one. But they all would fall on the line in these clumps. We're going to skip this analysis of variance part for now. Underlying this is this whole business of doing the inference. Is a model. Sometimes we said our data should be roughly normal, or at least not too skewed. That was a model that says what the data are kind of like, right? In this case, the ideal situation is y is related to some parameters, intercept, slope, plus some error. So the model says that between x and y there's some relationship, some linear line relationship. And then this error says that the points aren't exactly on the line, that there's this error about it. And the error is assumed to be normally distributed, centered at 0, so that the line's in the middle, with some standard deviation. Sigma squared is sometimes called the error variance. And so in linear regression, after you're fitting this, you want to look at the data. Does it really look like a straight line? Right? If it doesn't look like a straight line, you probably don't want to try to pretend it's a straight line. If there's big outliers in x and y, some odd points, that's going to affect the fit and make it harder to use this. We teach a class, Statistics 351. We're not teaching it next year, but we're going to teach it the year after that. That's about linear regression and linear models and many different varieties and things that come out of that. And so we could do many things to look at the assumptions. check model. Checking model assumptions is often done in terms of looking at the residuals, yi minus versus yi. Looking at the data, not the y's themselves necessarily, but maybe y minus their predictions. So we would want these sample residuals to roughly be normally distributed, so we might look at the histogram. We want them to have kind of constant variance, so we do a certain plot in a certain way. And so we kind of look at a few assumptions with that. So again, the mod is here. The residuals, we'll calculate these residuals from our predicted model. It'll calculate all of those E sub i's. Now if I plot those versus the x values, I shouldn't see any pattern. The residual shouldn't be growing or being smaller in certain areas or having any curvy pattern. They should just be random. So here are my x values before, here are these residuals. And so this looks great in terms of regression. There's kind of, the variability is kind of the same across the range. There's not any extra curvature pattern. There's just error. There's residuals that, that are kind of the same. So we kind of look at that. We might very well look at a histogram of the residuals. These are the residuals. I've called them the residuals here. And they look kind of normal. Right? That would be pretty good. Right? One other thing that comes out of this output from regression is there's something here called residual standard error under the R. So you can think about an estimate of sigma. Right? This extra error variance, how spread out are the errors? The estimate is sometimes written as the standard error related to the S's, the errors. The formula going from 1 to n is we square all the errors, add them up, and divide by n minus 2. It's kind of like dividing by n minus 1 for our sample variances, but we have two things we've estimated. Instead of just an average, we have to get the intercept and slope. There's two parameters. So there's kind of an accounting equation thing that goes on here. In probability theory, the average value of this under the model is sigma squared, so there's an unbiased thing. But it's the square root of that. So in R calls this the residual standard error. R. Different computer programs will give this thing different names. I don't think there's much consistency around that. But there's always something that tells you what that error variance is, or the standard deviation. In this case, if you look at that line, the residual standard error is 5.914 minutes. It's minutes because all the units are minutes. And so that gives you some idea of how variable the errors are, how far your predictions are from the regression line. So here's the residuals. Here's all those EIs. They're centered at 0. Right? So there's 0 in the middle. So how do we use a standard deviation to describe a distribution? Well, normal distributions, you get about 95. That's rolling. Where to go? About 95% of the values are plus or minus 2 standard deviations. There you go. That was about 5, 1 standard deviation, 2 standard deviations, 1, 2. And that describes most of the variability. So this next command puts some lines here, some vertical lines at those things. This the R commands, like the summary of it, really gives a list of all these different pieces that go into these different calculations of different sorts. And it's not sigma itself, it's the sample version. But that's the 5.194. So if you put those lines in here, so plus or minus 1 standard deviation, here's plus 1, here's plus 2 standard deviations in the error variances. We had 272 observations, so there's a few that are bigger than that, but not a whole lot. Right? That kind of describes that, the spread of those. What relevance did that have? Right? If we go back to our plot, say it erupts for 2 minutes. Our prediction was, what was our prediction? Whatever it was, we calculated it there. The prediction when it was 2 minutes here, 54.93. Well, if you come back right at 54.93 minutes, or 55 minutes, or even 54 minutes, are you going to be on the time always for the next eruption? Right? That's right at the line. Well, sometimes it happened sooner. Right? How much sooner? Well, if you subtract 2 standard deviations, it subtract about 10 or 11 minutes from that, you'll be kind of down at this bottom. Maybe you'll miss if it happens really early, then much earlier than predicted. But if you take that prediction minus a couple standard deviations, you're pretty good. Right? So the question was, if it erupts for 2 minutes, we predict 54 minutes as the eruption. If you show up at 54 minutes, about half the time you're going to miss it, right? Because it's already started. So how early should you come? Subtract a couple standard deviations out of that. And you're pretty good. Right? You'll most likely see it. If you're really concerned about being there on time, come 3 standard deviations earlier. Come 15 minutes before the prediction, and you probably won't miss it. So there's a sign there that gives this little thing. It's probably not quite this simple. They probably do a little bit more modeling, a few more variables involved in that, but it seems to work pretty well. We'll do a few more. Oh, it's checking normality. There's this normal probability plot. We want this to be kind of a straight line in probability theory. It's pretty good. The results are pretty nice. We will talk more about some of this other stuff, components of that output on Wednesday. And maybe look at a quick example of predicting with multiple variables. Here's one, trees. So this data set is a data set on trees. In fact, it's the girth, weight, and volume of black cherry trees. So these are 31 felled black cherry trees. And in environmental ecology, there are standards for measuring the distance around trees. There's I can't remember what it's called, a sept pole or some type of pole that you take out in the field. There's folding versions of it you can put in your backpack, and you unfold it and put it there, and it's something at 4 foot 6 inches, and you measure around the tree at that height, so that anybody out in any other forest is measuring at the same height, and you don't have the people that are 6 foot 6 measuring at different things than people that are 5 foot 9, 4 foot 9, or but they're all measuring at the same height around there, and so there's kind of an equal standard. So that physical, thing is important. Girth is the diameter around the tree in inches. Height, numeric height, maybe they chop it down and then measure it, or maybe they're doing something with angles to try and measure the height of these trees. And then volume, volume of lumber. So if you're cutting down cherry trees for commercial harvest, right, you want to know volume. Right? And we have height or girth or height. How can we predict which variable would be best to use? Here's a command called pairs. It does a little simultaneous plot of pairs of variables. Right, so this last row is most useful for us with volume, because volume on this going this way is on the verticals, on the y. This is volume, and then girth is on the x. So this is volume versus girth. This one is volume versus height, so you put height down here. Which of these two, girth or height, looks like it's going to be more useful for predicting volume?
Girth, because a lot more of the values are closer to the line.
Does everybody agree? Yeah, so these are all pretty close. there are some that got, there's quite a bit of variability in some of those things, right? So the volume scale is the same on both those two things. So it would seem that volume would probably be better. I would say this is a very strong relationship, right? And quite linear. Right? If you think about an equation for the area of kind of a cone or a column, right? It's kind of the girth, kind of the area of the base, like the pi r squared or something for the area of the base times the height. So the girth, the round, is directly related to the volume. They're probably not cutting down really short trees, and not really, maybe the ancient ones they can't cut down. They're cutting them down in a certain range that they can handle. So there's some uniformity there. So it works extremely well, right? If you look at correlations, trees has these three columns in here. So if you just type correlation of trees, it gives you this matrix up here. So it's a correlation of all the pairs, girth with itself, which is 1, it's like perfectly correlated. Girth with height, girth with volume, and then height with girth and height with volume. It's symmetric. Correlation doesn't care which one you're predicting. It's just strength of linear association. So we have 0.52 for girth. Well, let's see, we're interested in volume. So 0.598, almost 0.6 for height versus volume, but girth was 0.967. So it's extremely strong there. If you just wanted one variable, correlation versus there's that one. If you plot just that one variable. The summary command here gives the intercept of negative 36 and a girth of 9 there. So if you put that one, you can give it A and you can give it B, intercept and slope. There, it's going to put the predicted regression line on there. And that's kind of, probably good to check where it's going. This is the summary. We didn't talk about testing, right? But there is a t-test associated with it. A test of whether the slope is 0 or not. So hypothesis. And I know this goes kind of fast. We're talking about this. There'll be a homework assignment that if you look through the book and go work through a couple problems incrementally from the output, kind of gives you a flavor of this. Right? You can spend a lot of time on this. Null hypothesis is no effect. Slope equals 0, no association. No linear association, I should say, right? So this is symbols that was at beta slope. And the alternative is just that the slope is not equal to 0. To test this thing, we're going to calculate a t-statistic, which is just the sample slope over its standard error. And in this one with the trees, the slope estimate is 5.066, and the standard error was 0.25 roughly, and the t-value is 20. In this case, there were 31 cherry trees. And so degrees of freedom that we look at is -2 is 29. In -2, because we have both the intercept and slope instead of just a mean. Right, so two things have to be estimated to get to that point. The t cutoff value, the upper tail with 29 degrees of freedom, is going to be 2 something. But this is 20. From the plot, we don't have any question that there's a significant relationship. Right? Quantiles for the t, the big upper point here, and it was 29 degrees of freedom, 2.045. Right? If our statistic is bigger than 2.045, we'll reject the null hypothesis. There is a statistically significant relationship. There is a non-zero slope. We're convinced of that based on the data. the output gives us a p-value. This scientific notation means, practically 0. 10 to the minus 16th is a tiny, tiny number. This is about as small as it can represent there, so that's what it gets close to 0. And so girth, girth would be the better predictor. If you wanted to predict at a few points, like at 10 inches of diameter, you get a prediction there. Here's the prediction when it's 10. Right, here's the prediction when it's 20. So what I'm doing here is I'm just saving that predicted value as something called y hat, a little hat on it. Right? I'm just using the words that match that up and putting that there. There's a prediction when it's 20. What happens if you get a tree that has 5 inches diameter, or maybe circumference? I think this is. It was girth, so I should be calling it girth instead of diameter. It should be really girth. What if it's 5 inches girth? What is our prediction going to be? Negative 11.59 volume of lumber. Does that make any sense? Would you ever want to predict volume based on a tree with a girth of 5 inches? Are they ever going to harvest a tree like that? No, they're never going to harvest that, right? So 5 is outside of this range. Right? Maybe maybe there's a cutoff. That still seems pretty thin to be harvested. So with regression, it's really best to do it in the range where you actually see data. We don't care that the intercept is negative. It works out just fine for these ones that are big enough, right? And you're getting predictions that make sense there. But at 5, it just doesn't make any sense. Keep going. That extrapolation doesn't really work. What else is in there? Oh, this is the summary. Right. We'll talk more about some of this stuff. Next time, there's kind of an R-squared that measures the percent of variability to explain, and it's better, kind of like correlation. It's a lot better for the girth than it does for the other one. But on Wednesday, we'll do more with aspects of regression. Yeah, good. Thanks for letting me know. I see.
So I've been holding your book hostage for a little while.
Oh, okay.
I still have it and everything. I'm using it to.
Yeah, just keep using it as you need it for the project.
So the paper that I'm writing right now is not due till like April 30th. I'm still using the book a little bit for like some of the basic topics on K-means. I have a pretty good understanding of it. I would hope so. I have a presentation tomorrow on it. So, through development, no, because I was going to tell you, because the book really highlighted like the basic understanding of the method. And then when I went online, actually Oracle has this page about data science and all this stuff. They had examples on examples with like Python and stuff. And I'm very familiar with Python, so like being able to see how it looks like on paper on a formula versus like in software in a formula is kind of pretty cool in my opinion. And like that's like what my presentation's main focus is. But the paper is more about like the underlying statistical method, like the formulation and stuff. So that's why I started with book.
That's fine. That's fine.
Which
yeah,
I
keep it as long as you need it.
Yeah, that's why I wanted to hold on to it for a little while. I mean, I'll probably have it back to you within the week or so.
Okay.
I think
Thank you very
it's-
much. Yep.
Just want
Not a rush.
Just want to let you know I'm not hoarding it away or anything. It's definitely
Well, I
still.
still, you know, I still have to turn in your grade, so. you know.
Yeah. Still, hey, we're even. I'll make sure to bring it back to you. And I have the presentation tomorrow too, so if you want to come
Okay,
out
what
and
time
watch
is
it. I
that?
know. I think
Is that in
Three-
senior center?
yeah. So it's in the senior center. I know it's in the first door down the hall, but I think it's on at 3:30.
Okay.
And I'm pretty sure I'm going first. So if you want to stop in and let me know what you think,
Okay, bye.
feel free.
Thanks.
Thank you, Professor.
Thanks, Harrison.